on to the examples for equivalent dose rate. So we've already done equivalent dose, and what we would normally say is if you received a dose of radiation of around 4 sieverts, then that would be probably fatal. However, it does actually matter over the time scale that you receive that dose. So if you received 4 sieverts all at once within a few minutes, then that's almost certainly going to be fatal. But if you received a total dose of 4 sieverts over a period of a number of years, then you probably wouldn't notice it. So we need to think about not just the equivalent dose, but also how quickly you receive that dose. So we have this quantity called the equivalent dose rate, sieverts per unit time. And you, in this formula, unlike most of the formulas in physics, you have pretty much complete freedom over which unit of time that you want to use. So you could look at the sieverts per minute, the sieverts per day, or the sieverts per year. And you just need to keep a mental note of what your time unit is. So on to example 15. A doctor receives an equivalent dose of 120 millisieverts over a time of 3 years. So there's a slight error here, the word rate shouldn't be there. So an equivalent dose of 120 millisieverts. So H equals 120 millisieverts. Time, 3 years. And calculate the equivalent dose rate. So I can use my new formula, H dot equals H divided by T. Using the dot in this way just turns the quantity into a time rate of change. So it's the time rate of change of the equivalent dose. 120 millisieverts over a time of 3 years gives 40 millisieverts per year. Number 16. A workman receives an equivalent dose of 2 millisieverts over an 8-hour shift. Calculate the equivalent dose rate. So we've been given H is 2 millisieverts. Time 8 hours. And we're asked to calculate H dot. H dot equals H over T, which is 2 millisieverts divided by 8 hours, which is 0.25 millisieverts, but this time per hour. Example 17. A research worker receives 10 micrograys of gamma radiation and 50 micrograys of fast neutrons during an experiment lasting 8 hours. So the first thing we're being asked to calculate is the effective dose in microsieverts. So micrograys is absorbed dose, and microsieverts is equivalent dose. So these values here are given the symbol D for absorbed dose. So there's a few steps that I need to do for this, for part A. First of all, I need to look at the gamma radiation. And for the gamma radiation, I've been given a dose of 10 micrograys. Now the radiation weighting factor for gamma is 1. And you have a table of radiation weighting factors on page 11 of your notes. So there's the gamma there, and we're also going to need this one here for the fast neutrons, 10. So the radiation weighting factor for gamma is 1, and that means that we can work out H for the gamma, which is dWr. Write the formula, substitute in and then think about the unit. So if I have microgray, I will have microsieverts for H. And that takes care of the gamma. I need to do the same for the fast neutrons. So this time I've been given 50 microgray. And we said the radiation factor was 10. Times 10, so we have 500 microsieverts. Calculate the total effective dose in microsieverts. So we've got contribution from gamma and fast neutrons, so H total will be the contribution to H from the gamma plus the contribution to H from the neutrons, which would be 10 plus 500, which is 510 microsieverts. These are both in microsieverts, so I can just add them, keep it in microsieverts. Next part, calculate the equivalent dose rate in microsieverts per hour. So equivalent dose rate is H dot. H dot equals H divided by T. 510 microsieverts in a time 8 hours. And that works out 63.75 microsieverts per hour. We just need to think about the number of significant figures. So the information here has been given to one or possibly two significant figures. So really we should keep this to two significant figures, certainly not 4. So it looks like it's 64 microsieverts per hour. Let's try example 18. So this time we have a person who's working with radiation, and they have an exposure limit to their hands of 500 millisieverts per year. So the dose limit is H maximum permitted value of 500 millisieverts over 1 year. So what we need to do is work out exactly how much radiation the worker receives every hour that they work, and then work out how many hours that they can complete before they reach this limit. And it's complicated by the fact that we've got 3 types of radiation. We have gamma radiation, thermal neutrons, and fast neutrons. And so each of the 3 will contribute to the hourly dose received. So first of all, what we need to work out is the dose rate for each of the types of radiation, and we can use the formula H equals dWr, and we're applying that over the period of 1 hour, so it's 2 milligrays per hour, so it's dWr for every hour. So we'll do them for gamma first of all. And that's 2.0 for the dose, milligrays, radiation weighting factor of 1, so that turns into 2.0 millisieverts. and that's in a time of 1 hour. Then we have thermal neutrons. Now the thermal neutrons is 400 micrograys, so you've got to notice that that's a different unit. This was milligrays. 400 micrograys with a radiation weighting factor of 3 gives us 1200 microsieverts per hour, which is 1.2 millisieverts. You can multiply by 1000 to convert to millisieverts. And we really want to have everything in millisieverts per hour. The last one we've got is the fast neutrons. Now the fast neutron D is 80 micrograys. The radiation weighting factor of 10 gives us 800 microsieverts. And that's also for working for 1 hour. 800 microsieverts is 0.8 millisieverts. So now if this worker works for 1 hour, we can now work out the total that they will receive in or per hour. The contribution from the gamma, which is 2.0 millisieverts, and from the thermal neutrons, which is 1.2, and the fast neutrons 0.8. Add that lot together and we get 4.0 millisieverts per hour. Okay, so there's your gamma, 2.0 millisieverts per hour. The thermal neutrons, we had to turn the units from microsieverts per hour into millisieverts, multiplying by, dividing by 1000, sorry. And here the same, microsieverts to millisieverts. Add them all together, 4 millisieverts per hour. Now, over 1 year, you're allowed to reach a total dose of 500 millisieverts. So the question is, how many hours will you take to build up to 500? And we can just divide to do that. But we're actually using the formula H dot equals H divided by T. Now, we're building up 4 millisieverts per hour, so H dot is 4.0 on the left side of the equation. On the right of the equation, the maximum dose that we can receive is 500 millisieverts. And what we'd like to know is how long will it take to build that up. So it's T equals 500 divided by 4.0, which is 125 hours. So you can work for 125 hours before you reach that dose limit. Now, obviously no one's really suggesting that you go to work and work for a straight 125 hours. What that means in practice is that there's 52 weeks in the year, so 52 times 2 is 104 hours, so you could, realistically, you could do this job for 2 hours a week and still be within your limit, but you couldn't do it for much more than that.